I'm Tom, W8JI. This video is about using and adjusting tuning pulsers. Some will claim keyers sending normal fast dots are tuning pulsers. This isn't true. Normal fast dots have 50% duty cycle. If we look at the keyer output, which is the aqua trace, and the RF envelope, which is the yellow trace, we see the transmitter is on about 50% of the time. This won't even double the safe tuning time we have available. For example, if we had an AL811H amplifier that was grossly out of tune, the tube anodes might dissipate about 1,000 watts of heat when being driven with RF. The idle or quiescent no drive dissipation in the anodes might be 100 watts. The average heat is thus about 550 watts, or over twice the allowable continuous dissipation of the tubes. This will red plate the tubes and ruin them, even though we're using a 50% duty tuning pulser. On the other hand, if we look at a properly adjusted tuning pulser, we find duty cycle can be less than 10%. With a proper tuning pulser, we find the on time is less than 1 period, while the off or idle time is more than 9 time periods. The average heat dissipation is now less than 190 watts in this example, making the allowable mistune time unlimited. After testing different systems, including audio pulsing systems, I decided to use a simple battery-powered CW key jack tuning pulser. This pulser uses a single garage door remote type battery and has fully adjustable duty cycle and pulse rate. Grid current is the single most important tuning indicator in a grounded grid RF linear amplifier. The TOF module allows grid current to be read on all modes. This includes tuning with a tuning pulser. A good peak reading watt meter is required. The pulses should be as short as the meters and the radio's responses allow. The radio and the meters determine the minimum duty cycle. The rate should be between the upper speed limit of the radio and the lower speed limit set by the meters. Useful tuning pulsers have a weight or pulse duty cycle control, along with a pulse rate or pulse speed control. Optimum adjustment requires minimum duty cycle and proper rate or speed for the meter and the radio. You will find the best peak reading meters require some type of power source, either external or internal. Let's look at a few power meters and see how they behave. My reference power meter is a coaxial dynamics with a 100 watt element. My radio is an ICOM 746 Pro at 100 watts peak power output. For tuning applications, the Ameritron AWM30 is one of the better peak reading meters on the market. I designed the AWM30 peak reading system for a very fast attack and moderately slow decay speed. Note the peak reading is stable with speed changes. If the radio peak power output is stable, the meter is also stable. The AWM30 tracked the coaxial dynamics and the radio over a wide speed range. The AWM30 is a great meter in PEP speed tests. This next test shows how the radio's peak power becomes unstable when the pulse rate reaches the response limit of the radio. At some high speed, the radio cannot follow the pulsar signal. I'll slowly increase the pulse speed or pulse rate until the radio no longer follows the signal. We don't want pulsar speed too fast for the radio. It's better to have it on the slow side. The next test shows how average power or heating changes with pulse width. Peak power is stable over a wide adjustment range, but average power changes a great deal with duty cycle and pulse width. For this test, the meters are set to read average power. Higher duty cycle or more pulse width directly increases the average power and the heat. Higher average power means more heat and more risk to the amplifier. The speed doesn't matter too much as long as it's slow enough that the radio can follow the pulses and fast enough that the meters don't sit there and bounce around with each pulse. But we want the minimum pulse width or the minimum duty cycle, the lowest possible average power. Using a 50% duty cycle, like in a normal keyer set for fast dots, won't gain you very much at all for a tuning pulsar. We want short pulses with a lot of time in between pulses, and we want meters that read peak power accurately. I have videos of a few other meters that I tested. The Heathkit HM2140 is a pretty good meter for amplifier tuning. The old Heathkit meter is actually a pretty good meter for using with a tuning pulsar or for reading peak power in normal amplifiers. This Daiwa meter is just sort of so-so. It's not a really good meter. It's not a horrible meter either. This Daiwa NS660 meter has a few problems. It reads a good bit low. The hang time is much too short on normal peak settings. The hang time is way too long on hold peak. And the SWR calibration in this particular Daiwa sample meter was pretty far off, almost useless for reading SWR. This giant MFJ meter is an example of a completely useless meter. The MFJ 869 is easy to read and looks great, but the firmware makes it useless for tuning amplifiers. The pointer just sits there. I mean, what's with that? You couldn't possibly use this meter to tune anything. This meter behaves no better when it's set to average power. It's still all wonky, so it's not even useful for reading average power. This is what happens when the software guy writing software to read peak power and average power doesn't understand how the system works, and nobody else later on follows up to be sure that the end product works the way it's supposed to work. I hope this video is useful. All good tuning pulsers should contain a duty cycle and a pulse rate. The rest of the stuff can vary from unit to unit, but it's very important that you have both duty cycle and pulse rate controls on the tuning pulsar.